Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing the theories of theory of relative reliability, and we are discussing the reliability in connection with this spacecraft mission. So, let us have a recap of the last session. So, in the last session we discussed the system reliability. So, we consider the subsystems in series. So, in series means all the subsystem it is required that all the subsystems should perform satisfactorily, then only you will have the system performance. Means that the no components in the chain which are in series should not fail. So, it is basically a case of it is the end, that is in the Boolean algebra or in the probability theory we use the term that is the end operation. So, end means it is the multiplication, but of course, we can multiply it directly whenever we consider that each system is independent of the other. So, whatever I said, the system success, that is the success of every individual component, and the failure rate which is also constant if we consider the subsystem failure rate is constant, that is we consider lambda I is the failure rate of the ith element or ith subsystem. So, in that case we can show that considering this, that is the failure rate of this system is the algebraic sum of the all the, that is the subsystem failure rate. Then if you like to calculate the mean time to failure. So, mean time to failure whenever this is the failure rate is constant, you can show it that mean time to failure is given by 1 by the failure rate. So, in that case you will have the failure rate 1 by the summation of the failure rate of the individual subsystem or the element. Then we consider a case of considering two elements in parallel, and we said this is the redundant. Redundant means any one the system will work if both are working or any one. It will fail whenever both are both this element 1 and 2 fails. So, in that case we say that is if I consider the failure. So, system failure will be means it will fail whenever both the system fails. So, from there we wrote it is 1 minus R 1 minus. So, we wrote this is equal to 1 minus R s, okay, and then the R s we wrote 1 minus. So, it is 1 minus R s. So, I can write this is equal to 1 minus the f 1 into f 2, or so R s is equal to 1 minus f 1 into f 2. So, it is 1 minus R 1 into 1 minus R 2, and then finally, we got an expression R 1 plus R 2 minus R 1 into R 2. So, whenever I say here also that is each element is having constant failure rate. So, I can write that is the system reliability in terms of the failure rate like this one. So, now we will consider again this static redundancy of this two element. We will calculate we will find the expression for his MTTF, then failure rate. Okay, this part already we have done it. We will find it the failure rate, this is already done, and then we will consider n systems in parallel, and we in fact we will use whatever we have derived for the two system, that will be useful for us to have a general the expression for the reliability of the system when the n systems are in parallel. Then we will consider that is the reliability if k out of n elements are necessary. So, this will also we will cover today. Okay. So, let us find out this MTTF. So, so this is our I think it is okay, okay, it's already there. Okay. So, considering this, you know, the subsystems are independent. So, we were able to write R is equal to R 1 plus R 2 minus R 1 into R 2, and then we wrote this is as E lambda 1 t, then E minus lambda 2 t, then minus e to the power lambda 1 plus lambda 2 into t. Okay. Now, we like to find out this MTTF. Now, since this is not in a form of a single exponential term, so we need to find the MTTF from the this whatever we use the equation in our last session, that is T and then the failure rate T f t dt. So, this gives you the minimum MTTF, that is the mean time to failure, and we have seen that this I can write 0 to infinity R t dt. Okay. So, we need to integrate this term. So, if you integrate this term, so you will get the first will this term will give you it is 1 minus lambda 1 t by lambda 1 minus then 0 to infinity, then you will have the other term lambda 2 0 to infinity, then minus, then it will be plus, then e to the power minus lambda 1 plus lambda 2 t divided by lambda 1 plus lambda 2. Okay. So, this gives me 1 by lambda 1, okay. Then this I get plus 1 by lambda 2 and this will give me. So, this I will do from 0 to infinity 1 by lambda 1 plus lambda 2. Okay. So, now, if I want to calculate the failure rate, so again we will use the for the failure rate. So, failure rate H t is given by F t by R t. So, what is F t? F t I can write in terms of R t, that is minus R dash t divided by R t. So, already I have R t is equal to e to the power minus lambda 1 t plus e to the power minus lambda 1 t plus e to the power minus lambda 1 plus lambda 2 into t. Okay. So, now I can write my H t is equal to, using this equation, H t will be equal to minus R that is the derivative of R t. So, I am to differentiate each term here. So, if I differentiate this one, so I get the first term as minus lambda 1 into e to the power minus lambda 2, then this is 2 lambda 2 t, then lambda 1 plus lambda 2 . So, this becomes e to the power minus lambda 1 plus lambda 2 into t divided by e to the power minus lambda 1 t, then e to the power minus lambda 2 t, then there is a, so a negative sign will come here. Okay, then minus e to the power minus lambda 1 plus lambda 2 into t. So, this I can write as lambda 1 e to the 1 minus lambda 1 t, then lambda 2 e to the minus lambda 2 t, then so here it will minus sign will come. Into t divided by okay. So, you see here whenever we are putting the systems in parallel. So, you know, although each element has a constant failure rate, but the system failure rate or hazard rate failure is a function of time. Okay. So, now we will consider a general case, okay. But before we write and that is the or we derive for the general, it is do by the theory of mathematical induction. So, we have done already for 2. So, now we will do for 3, then it will be easier for us to write a general expression here. So, let us consider the case n is equal to 3 here, n is equal to 3. So, if I consider n is equal to 3, then my system reliability R s t will be equal to 1 minus f 1, f 2, f 3. So, what then again the similarly the way we did it for the 2 subsystems in parallel. So, it will be 1 minus R 1, 1 minus R 2, 1 minus R 3. Okay. So, if you do this algebra, then it will be R 1 plus R 2 plus R 3 then minus R 1 into R 2 then R 1 into R 3 then minus R 2 into R 3 then plus R 1 into R 2 plus R 3. So, you will find some similarity whenever we are taking 2 system, it was R 1 plus R 2 minus R 1 into R 2. But as it will increase, so but there is a what is called there is a trend. So, we will use that trend in order to find the the MTTF and the hazard rate, all those things. So, now if I take a general case, so I can write the R s t is equal to 1 minus multiplication of or the product of the n element 1 minus R I. So, you have seen that is for if n is equal to 3, then I have my R s t is equal to R 1 plus R 2 plus R 3 minus R 1 into R 2, then R 2 into R 3, then R 1 into R 3, then plus R 1 into R 2 into R 3. Okay. So, this is the thing we have written. So, now if I want to find the MTTF of the system, MTTF of the system will be equal to. So, I can again doing the integrating this, if I just integrate this, then I can write RST. So, I will write RST first. So, it is e to the minus lambda 1 t, then e to the minus lambda 2 t, then e to the power minus lambda 3 into t, then e to the power lambda 1 plus lambda 2 t, then minus e to the power lambda 2 lambda 3 into t, then minus e to the power lambda 1 lambda 3 into t plus e to the power lambda 1 plus lambda 2 plus lambda 3 into t. So, now if I integrate this, then I will get the MTTF. So, I need to integrate this 0 to infinity dt. So, I let me integrate a 0 to infinity this whole this term dt, then I will get 1 by lambda 1 plus 1 by lambda 2 plus 1 by lambda 3, then 1 by lambda 1 plus lambda 2, then minus 1 by lambda 2 plus lambda 3, then minus lambda 1 plus lambda 3 plus 1 by lambda 1 plus lambda 2 plus lambda 3. Okay. So, now I will consider, suppose all the subsystems have similar, if all the subsystems has the same failure rate, has the same constant failure rate. Constant failure rate, and we will put it that is lambda 1 is equal to lambda 2 is equal to lambda 3 is equal to lambda I. So, then I can write the MTTF as, so it will be 1 by lambda I plus 1 by lambda I plus 1 by lambda I. Okay. Then twice lambda I, okay, then minus lambda I. So, 3, then 1 by 3 lambda I. So, now what I can do, I can simplify this to write, it will be 1 by lambda I plus 1 by 2 lambda I and then 1 by 3 lambda I. Okay. This I can write, this is equal to m t, that is the minimum time to failure, okay, of any f. Okay. Then the second one again MTT by 2 plus by 3. So, this is we did 3 and for 2 also I wrote, that is MTTF is equal to, we found it is 1 by lambda 1, then 1 by lambda 2, then minus 1 by lambda 1 plus lambda 2. Okay. So, if I use that is lambda 1 is equal to lambda 2 is equal to lambda I. So, if I write that, then MTTF for 2 will be equal to 1 by lambda I plus 1 by 2 lambda I. When n is equal to 3, we got MTTF is equal to 1 by lambda I So, by using mathematical induction, I can now write if there are the n systems having identical the failure rate okay, or the having identical of the n elements, okay, then I can put the MTTF is a general expression I can write. So, what we will do? So, in this case if the failure rates number of the element of the elements in parallel are constant and identical and if correct operation is ensured, I is correct with a single element, then I can write the MTTF of the system MTTF, and write it like this. MTTF will be given by. So, I can use this this mathematical induction and then I can write it 1 by I, then I can use 1 by okay. Then I can use was 1 plus 3 lambda I okay. And like that I can go up to 1 by n lambda I. So, this is basically the MTTF of MTTF, then MTTF I by 2 I by 3 plus MTTF by n. So, this is the way we can calculate. In the other case, in the series case it was very straightforward, but here since we are dealing with this type of parallel thing. In fact, if I consider all the things are different also, then also you can find the expression, but that expression will not be so simple. So, if you consider that is all the identical systems having the identical failure rates, then you can write it like this. Otherwise, the most general expression you need to write it. Okay. So, we will take just one example and see. So, just if I consider two elements in parallel, having identical failure rate. So, this can be given some value, but we will take here the general one. So, in that case the MTTF will be equal to 1 by lambda I plus 1 by twice lambda I. So, you are getting 1.5 times the MTTF of the individual, and this is the system MTTF. If you take 3 elements, 3 parallel elements, then MTTF it will be 1 by lambda I, then 1 by twice lambda I plus 1 plus 3 lambda I. So, this will be equal to 1.83 times lambda I. So, you see this is your mean time to, that is the failure that is increasing, 1.3 of the MTT. Okay. Now, we will consider, that is we will consider as that is for the correct operation, we will consider that is. So, we will consider that is k for correct operation of a system, for correct operation of a system of a system of a corresponding k elements are k elements needed to k elements out of n elements needed to work, n elements needed to be to perform successfully. So, here we will use the binomial, the binomial theorem. So, I will just take, I will write first then explain. So, I can write this as 1 minus so, it will be R of I, and it is 1 minus R of k I. Okay. So, in the next class we will further discuss on this, that is there will be the some systems where you need a minimum number of components to be that should suppose if you are having some 3 systems, say the redundant system or 3 systems in parallel, then minimum you need maybe that is 2 should work. So, in that case how to calculate the system probability will discuss in the next session. Thank you very much.